Let's talk universal gravitation. Okay, we've been talking about energy, gravitational potential energy, kinetic energy, and elastic potential energy. I want to focus a little bit more on the potential energy due to gravity. Okay, potential energy in general is an energy that is dependent on a force being applied by another object, right? A spring has potential energy because of the forces within the spring. Why does an object above ground That's not ground. Why does an object above ground have potential energy? Why does it have that stored ability? Well, it comes from the attraction between this object and Earth, right? We don't think of Earth as being a big round block usually. We think of Earth as being a flat surface, but Earth is a giant spherical mass, and there's this an attraction between all objects with mass. We call that attraction gravity, okay? And so gravity acts to pull this thing down. So the reason there's energy here at all is because there's a force of attraction between them, and to make this the most stable, to get it into the least changeable configuration, this object needs to be sitting on the ground. Okay? So the potential energy, this from gravity, this arises from the attraction between mass. And that attraction is something we take for granted, but it's between all masses. Okay? Arises from the attraction between mass. All mass attracts all other mass. Okay? It's not just the Earth that attracts objects. You have gravity too. Okay? And that was what Newton's gravity law really said. Okay? Isaac Newton did not discover gravity. The first guy who fell and tripped and landed on his face, he's like, okay, there's gravity, right? What Newton did was he discovered that gravity is universal. So there's actually not just potential energy for something a little bit off the surface of the Earth. There is gravitational potential energy between us and the sun, right? And so how is gravity related to, or the force of gravity related to what's causing it? Okay? Well, it comes down to an equation that Newton developed, and basically it says the force of attraction between two objects with mass is given by m1 times m2 divided by the distance between them squared times the gravitational constant capital G. Okay, this capital G is 6.67 times 10 to the negative 11th, and this is Newton meters squared per kilogram squared. It tells us how big the gravitational force of attraction is between all objects with mass. You'll notice this times 10 to the negative 11th, that's really small. Okay? We don't have a very strong force of attraction between us and other objects because our masses are really small. But I want you to think about this on the surface of the Earth. Okay? If you have the Earth, and we're going to call it M1, okay, and you have an object sitting up here on the Earth, we're going to call it M2, then what's the force of attraction between them? Well, F equals M1 times M2 divided by the distance between them squared times G. So is this distance zero? Is this force infinite? No. This force is measured between centers of mass. Okay? So in this particular one, this becomes the radius of the Earth, because the distance between something on the surface of Earth and the center of Earth is the radius of the Earth. Okay? And so if we knew the mass of the Earth, we could actually calculate the acceleration due to gravity independently of measuring it. Okay? So what we're going to do is we're going to take a look at how that would work. The force of attraction is the masses. So if this mass right here is a mass of 5 kilograms, okay, and Earth has a mass of 5.97 times 10 to the 24th kilograms, okay, then, and the radius of the Earth, I got to look that one up real quick. The Earth's radius is 6.38 times 10 to the 6th meters. 6.38 times 10 to the 6th meters. Okay, then we can plug all these numbers in. Okay, and we get 5 times 5.97 times 10 to the 24th divided by 6.38 times 10 to the 6th squared times 6.67 times 10 to the negative 11th, and then we'll get out of this the force of attraction. Okay, and if we do all that, let me work that math real quick. So if you put all these numbers in on your calculator, it magically pops up with the answer 48.91 newtons. Okay, now we didn't have to do all that math. We already knew this gravitational attraction. A 5 kilogram mass on Earth, the force that acts on it is ma. So the acceleration due to gravity is 5 times 9.8, which equals 49 newtons. Okay, so those are the same. Why does this equation work, and where did this constant come from? Okay, well, that constant was measured by Cavendish with a special balance. But as for why that equation works, if I have the force acting on an object is ma, and I also know that the force, and this is caused by gravity, then really this is mg, right? So this is m1g, where this is the object out here, and this is the Earth. Here's my object, m1, m2, right? So this equals m1, m2, g divided by r squared. And so you can see this is why the acceleration due to gravity is constant for all objects. Mass cancels out of this. Okay, and the only thing g depends on is the mass of the Earth, the universal gravitational constant, and the distance. Okay, so g is constant for things that are close to Earth. Now if you get further away, g actually changes. Okay, and we'll do a couple problems with that, but I want to show you where this gravitational constant comes from. Okay, what a guy named Henry Cavendish did was he actually measured this by taking two big masses and setting them on either side of a bar. And then he suspended from the ceiling another set of masses that were free to rotate. So this could rotate this way and this way. And they pulled towards each other until the tension in this cable from the twist balanced the force of attraction between these masses, and he was able to measure capital G. So capital G is different than lowercase g. It's the universal gravitational constant. Little g is the acceleration due to gravity. Okay? So we're going to use this equation today to study energy and force between masses.